So, hello everyone. Welcome back to the computer vision classes, online classes. We will be now moving into another new topic, very interesting topic and very important topic. This is about interest point detection. Okay, this would anyway would become clear to you as we move on in this class. So, before going into any of the details about that, let me pose a problem for you. Suppose this is the kind of the image I want to build, which you all know is referred to as panoramic view. While your camera could see only to a particular region, you can take multiple, but you want to have a view or an image that spread across a larger angle than what your camera can focus on, right? So how you could do that? What is the way you can do this? How can you build such image? Can anyone shed some light? Don't tell me that in your mobile you will switch on panoramic view and then I will take. You say it more technically. Of course, at the end you might be doing a similar stuff, but this is the problem posed to you. You are given a camera. Your camera at a given instance can see only portions of the whole scene, but you want to construct the whole scene. How do you do that?
So we take the images
Hmm.
at certain angles,
Hmm.
covering the whatever the field of view you want.
Right.
But each image should have a some overlapping between with the previous image,
Right.
so that we can have some common information
Hmm.
while merging the two images.
Very good. Very good. So what you do is, this is all I'm sure every one of you would have taken this panoramic view images, which is present, I guess, in most of the today's cameras, today's cell phones. So if not, just move on to the panoramic view and take the picture where you would be putting your camera in the panoramic view camera of your mobile, and then would be moving like this. In another way, assume that that feature is not there. You are, instead of being given a cell phone, you are given a camera which can take only still photos. Okay, so you could take one picture, as one of you have rightly mentioned. You take a picture, you move it a bit, take one more picture, but while making this picture, make sure there is some overlap with the earlier picture, right? And you repeat the whole process uh, from the starting angle to the ending angle, for which you need a panoramic view. Then the next question comes to, now how do you align these images? That's the question now for you. Now you have, let's say, you have 10 images now, starting from the beginning to the end. Okay, now you also know the sequence, so you just need to align two images at a time. That information also you have it. Now how do you align those images?
Maybe you can calculate the transformation, some homography matrix like actually between two.
Right, so you need to compute some transformation between that aligns one image with the another image. Okay, now what is, that's a very good answer, that's the right answer. Now the next question, logical question, is what is the information in a given image that you want to use for computing this transformation? Or let me slightly rephrase my question and put it slightly differently. If I give you two images, okay, let's say I have given you these two images. Okay, you could see here, this is kind of a left side of, so this compared to that, you moved it here. Now I all you need to do now is just the assume that I have not tilted, assume that there is no zoom factor involved. So the transformation here that aligns one image to the other over the overlapping region is just a shift in the x, or forget even that in y you have put your, you have not moved your camera at all. there is only a movement in the x direction. So how do you now align these two images? Then only you will get the full view, right? You could visually see that this in fact corresponds to this region, right? And this is to the right side of your scene, and this is to the left side of your scene. I want you to merge these two. How do you do that? How we as humans do it? First, you tell me that.
Some points like corners or something.
Very good. So corner is yeah, is a spot on answer here. Or let me call it a slightly different name, because corner is not just the only thing we look at. Let me call it as some key points you are finding out, or you are looking in one image, and to the other, within the other image you are trying to match that. Like for example, here you would see there is a big peak here, right? And this is having the same white region here. And then you can say that, well, this peak here should match with this peak, that's you could say. And similarly, you see here one peak here, similarly that should match here, that you could say. Similarly, you can say that, well, this region, for let's say somewhere here, should match with this, that you can say, right? So these are the kinds of points as a human we would look at. Again, there is a kind of trough here that should match with something like this, right? It is after getting these things, you would now could put this in correspondence with this, right? This in correspondence with this with here, this with here. Now you move this image such that these points would match. Is it not? This is the manner we are kind of doing the matching. See, we could have taken the whole information in the image and could have used a metric like mean square error of intensity differences. Again, mean square error is very sensitive to scaling in even intensities, intensity values, simple scaling. So maybe normalized correlation you can call. And you could have done, you could have taken the entire image and do that. Okay, that is what we have been doing so far. Or the next method after the whole thing we have come across is taking the edges, but edges is not really the, if you take the whole edge stuff like this, okay, you, it's not really, because there is some information here which is not present in this other image. Similarly, this information not present in the other image. So, well, edge is again not really the way we as humans are using that. So hope you have already noticed that we are slowly moving from using the entire image. That means by entire image I mean every pixel intensity. From there we have come to edges, which are like gradients in the image, where you have significant gradients image, to the point where you select some key points, okay, and use them for describing an image or for characterizing an image, right? Is it clear so far?
Sir,
Yes.
you've mentioned that like are these points the corners, or are there other kinds of points as well?
Well, one thing is corners are definitely one candidate there, but corners need not be the only points. Okay, just remember this statement I am making, which you would eventually become clear, and I would again come back to this point and answer your question that time. Okay, so corner is definitely one point, but need not necessarily be the only point that we use. Now we are doing it very intuitively, that we are able to find out which are the points that would kind of represent the image quite well, and that could, for which we could find mapping in the other image. But since we have to now implement this using an algorithm, isn't not? So while finding out some key points, we should come up with a set of properties that these key points should satisfy, so that we could have a very good alignment, or mapping of these two images, so that one application we have started with is panoramic view is appropriate. Now, what do you think should be the desirable properties of finding out these key points? Or let me also make it more specific. Assume that now I have an algorithm. I run that algorithm on this image. Then the same algorithm, then I want to run on this image. Once I run it here, it should give me some points here. This algorithm should give me some points here, okay, like this. Similarly, when I run the algorithm on that, it should give me another set of points, okay. And I should then, if I find out correspondences between this set of points to the other set of points, then for the time being ignore about those points which are present only in this image or in this image. Assume that once you have take computed or considered here enough number of key points, those points which are there only in one of the images are negligible. That's what you assume for the time being. Don't ignore about that, okay. Now I also give you a magical algorithm, okay. It's not magic. We would discuss those algorithms as well as we progress in this course after few weeks. Assume that I give you that algorithm that computes the mapping also between that. That's not your job now. Your job now is to come up with an algorithm that gives you these key points in a given image. That's the like work that we need to do, right? That's the job at our hands right now, okay. Now, before actually coming up with an algorithm for that, what are the desirable properties for this key point detection algorithm that you think? So I run that algorithm, as I said, on this image that should give me these points. I should then run it here and then find. I have an algorithm that if I dump, this is one set of key points from image one and set of points image two, that would give me the mapping. That I don't have to worry about now. I have to worry about the algorithm that gives me these key points. Okay. Now, what are the desirable properties of these key points given by the algorithm?
Like you've told corners, for example. So if we identify a corner, maybe we can identify the angle uh, of corresponding to that corner with some accuracy, so that in the angle measured in both the images will be the same.
Okay. Uh, yeah. Just define your desirable properties based on one image, for example. Okay. Let me even simplify further. I give you just this image twice. Okay. You run that algorithm once. You run the algorithm second time, and you try to find the mapping. So, what are the kind of, see, while mapping? It is not like so there are certain things you look for. What are the kind of properties you would desire here? Each point should have its own unique signature, okay. So for example, your class is sitting, or the width of your class is very high, okay. For some reason we made it like that. So I took a picture here, okay, for half of the class. Now for the 1/4 overlap, I have taken one more picture. When I want to map them, right, each person, if I'm looking at the persons, if the person is unique, okay, if I could identify this person uniquely, then only I could find out the matching. So each point you should be able to uniquely describe that point, right? You should be able to uniquely represent that point. That's one thing. Second, or even I would say the first one is you refer to it as repeatability. This is a very important property here. For example, when I run the algorithm here, if it gives me a point here, as long as here also this information is there, it should always give me that. It should not do, the algorithm should not be randomly or some varying heuristics. It should not be giving me some other point. And then once I get this point, I should be also able to uniquely represent that point. That's very much important. Whichever key points I'm taking, I should be able to uniquely represent that point. Suppose what I mean by saying that I should be able to uniquely represent that point is, suppose I got some point here. Okay. Now, well, that probably, let me show a point here. I have a point here. Even visually, as a human, we can't see here and say to which location it maps, right? So there should be, this point is not a good candidate for your algorithm giving a point here, because there is no uniqueness in which you can describe that point. Well, you might ask me, what do you mean by representing a point? Okay, this is something again we discuss in more detail, and we have the next algorithm is in pipeline after we go through few classes. Okay, maybe next week or the week after that, you would see a point algorithms to how you represent given a point, how you efficiently represent that. But for the time being, let's not wait for that. Let me give you some way of representing it, which is not necessarily the best way. Of course, it's not the best way. Is, let's say I represent that point by taking just a window around that region. Okay, and now if I take a region here, see this point also I could represent with this, but for that I need to take a very large window. So what is the problem in increase? And then even a point here, okay, where there is no variations here, okay, matching here, okay, this might be going here. I could still find out if I take a bigger region here and look for correspondences there, or look for maybe a mean square error, assuming the intensities are same. I could, by taking a bigger window, I would still be able to later find a mapping between them. But what would be the problem when you are increasing your window size for representing a given point? I made a statement here that point should be uniquely represented. And then I made a counter statement or somewhat counter statement there, that you could perhaps represent a point which in a narrow region might not be unique, but you take a bigger window and then it becomes unique. That's the something I made. Then I'm again posing now, what is the problem in going on increasing the window size? Is there any problem other than computational complexity? Do you see any other practical problem here?
Sir, the points immediately next to each other might
Hmm.
not be uniquely identifiable if you take large window size.
Well, for
Both
that
of them
window
might be
again, I
identical.
will take a larger window. You are in fact in a way right. Okay. Other than that, any other point? This is my assume that that's an interesting point there. Okay, that's having mapping here. Now you tell me what could be, what is another desirable property? Why we could not have? Why it should have a compact
We might
description?
have lost the windows, part of the window that we considered in the first picture and moving to
Right.
the picture.
Right. When you are moving it, see if I take a window like this, okay, assume that there is something also, or maybe if you look at here, that would make your things easier, but that's okay. Information that is there here, this portion might not be there here. See, or the object itself might be going, this is one application that we are talking about, but it is, you will see shortly, this is not the only application for which you require some key points or a feature points. There are other applications. For example, an object is moving, you want to keep track of it in multiple frames, so the content could be changing as you move on from one image to the other. Maybe other vehicles are coming on the road, you're trying to keep track of a vehicle. And now if you, for uniquely representing that particular vehicle, if you are taking a larger window, this content could be varying from one image to the other image. So compactness is another very important property, that we are not going yet to the algorithm, we are just looking at what are the kind of properties that you would require. One is repeatability, as you said. Say this is the same example. When I run it on image one, if it is giving this point, but the same point is in fact here, but it cannot find out that point here. the algorithm is not giving here, then there is no way you where to map this. There is no way you could map it. So the first important and most important thing is repeatability is there. The second one is your descriptor should be very distinct. So as I said, in the snow, for example, if you take a point, you yourself, when you are looking at just that one point, you have no clue on where to map it if you are just looking in the local region, unless you are looking at a very large region carefully and then finding out the mapping. So your descriptor, how you are encoding or how you are characterizing that particular point, that what you mean by descriptor. Again, this would become more and more clear as you move on, but for now assume that descriptor is something just simply a window around that point which you are looking at, and the intensities, that patch should be the same. Okay, that for now you consider as the descriptor. It has to be reliable, so you should have kind of unique matches possible there. Okay, so that's called as, first one is called as repeatability, as also referred to as precision. Say matchability should be there. Then, as I said, compactness and efficiency. Okay, these are again a feature occupies a relatively small area in the image, robust to the clutter and occlusion. So that's the locality, what you mean that. Then how many number of features? The compactness is slightly differently, the term compactness is used in a slightly different meaning here. When we say compactness here, it means the number of feature points or the number of key points you are getting. See, if you require to use every pixel at the end, under an extreme condition, if you had to use every pixel in the image, okay, to represent that image efficiently, then there is no point in calling them as key points. So it is like everybody in the class is ranked one. Okay, it doesn't mean that everybody in the class got the S grade, the outstanding grade. Doesn't make any sense. Similarly, so you should be able to characterize an image with least number of points, minimum number of points. That's what we mean by compactness, so that you are computationally, this is more tractable. You could do things at a higher scale with more number of images. So although we have not yet looked into any algorithm so far, what we have seen so far are, suppose I'm going to characterize a given image with a set of key points. So these are the representatives of your, so you are going to represent your batch. Okay, in one of the committee meetings, you send one representative, let's say, or let's say 3 4 representatives. We are now discussing on how you, we are not yet discussing on how you choose them, but what we are discussing them so far is what are the desirable properties for those representatives. That's what we are discussing. So one thing is repeatability, matchability, compactness, and locality. These are the 4 important features, desirable properties of these key points. Clear so far? Any questions so far?
Sir, I have one question.
Yes.
Now, these two images, what you are shown is has the same intensity.
Mm.
It
Mm.
happen when we take the different clips,
Mm.
the overlapping area though, but other may have some more like a tree shadows and all in which
Correct.
something and
Correct. That is quite possible. So that's what, even assume that there is a intensity difference has come out by the moment you have taken the first snap here, moved your camera and took the second snap. Still, that's what we mean by repeatability. Even because with those changes, if you have took a point here, it should still give you a point here. That's what has to happen here. That's what we mean by repeatability also. It's not necessarily just the change in the viewpoint slightly, but it could also should carefully take into account. You should be finding out, your algorithm should be able to give you the same point despite some changes in intensities, despite some occlusions happening while you are taking, despite having new area added, new region added to it, and of course despite having some area got eliminated. But of course this as such directly this cannot be addressed, but the way we address it is, what you do there is unless you find out a mapping here, whether there is a map or not, mapping or not, if there is no mapping, you won't consider it by in the process of alignment. That's how you take care of this occlusion in one image and addition in another image. I should not be calling it as an occlusion. One region is present here and it's not present in the other image. That again, we will come back to a set of algorithms for dealing with those points a little later. But hope, yeah, I hope that is answering your question, right? It should take into account those aspects as well. What I'm saying is your algorithm should be able to detect those points like corners, not just the corners, but points like corners are something you could very uniquely identify, right? So those are the kind of things your algorithm should be able to detect. And again, detect not in one algorithm, but repeatability also should be there in its detection. Let me tell you some more examples where this key point detection could be useful. You have already seen now one application could be getting a panoramic view, where you have taken snapshots of a scene, a bigger scene, like a landscape, and then you are going to stitch them together. And another one is image alignment. Let's say now the same object, you might have taken different images. Okay, this could be, for example, in the remote sensing, you are getting before and after some havoc has happened in the recent time, they were showing you the images. So you have the earlier image and now the current image is there, you want to align them. Okay, also referred to as registration. While you are doing registration, one way is you consider each and every pixel information there, intensities or some other features extracted from it. Or more meaningful thing would be to find out some key points in each of those images and then register those images. Okay, homography or fundamental matrix, since we have not yet discussed these two, I postpone the description of them for a later point of time. We will come back to that while we are registering, while we are discussing about registration. Another thing, 3D reconstruction of a given object. See, the moment you are taking a picture, the 3D information is now smashed onto a 2D screen or a 2D plane now. From that, if you want to construct the 3D information, you need to do a different kind of alignment there. And also there as well, you need to find out how a particular, for example, the way we see the 3D is when you see an object, like the depth that you perceive here versus the difference of depths you would be looking at, for which you need to align the images coming from the two images. Okay, again, I am what I am saying is not at all a complete description. Again, I am postponing it for shape from stereo part, and also maybe if time permits, active stereo method like fringe projection also you'll see. But anyway, the message, key message here for now is 3D reconstruction also requires finding out some key points and finding a mapping between them. I already talked about the motion tracking part. You would like to see from one frame to the other frame, for example, a given object, how much it has moved. So you need to find out some points, key points here. You find out some key points in the other frame, then you see where it has moved. And that would give you, depending on your frame rate and how the pixel mapping to the spatial mapping transformation that you need to take. Okay, and many other aspects. Once you find out this mapping, you would be able to see, do the motion tracking where where this has moved, or you could do a forecasting of its motion on where perhaps it would be roughly moving in the next frame. And of course, similarly, in similar lines, you could do object recognition also, it would require. And then robotic navigation, you want it to be navigated, you want to represent the entire scene with some key points. It's not like for something which has to work in somewhat real time, you cannot consider the entire content of the image. That's one aspect. Second aspect is a robot has to move in the three-dimensional space, whereas the eyes for the robot, which are cameras, are in 2D. So that inside that also there is some mapping that has to happen. Okay, these are certain applications of it. Now we are going to look at why, what would happen if a point is there in a uniform region versus a point is there at a corner versus a point is there around an edge versus a point is there at a corner. So I'm sure based on these images itself, you'd be able to give some interpretation and intuition on what would happen if your key point happens to be a point in the uniform region, your key point happens to be a point on an edge, and your key point happens to be a point on a corner. First, let us start with this case where you have a point here. What is the difficulty with that? If you have, if I give you, okay, this point, okay, don't think that this is the region. This is just I'm considering a window around that point to represent that. That's the window. But inside this whole thing is dark. That's what you consider. If I give you this point as a key point, what is the problems that you are going to encounter? See, first thing is repeatably, if you want to find out a point on the same image, if you have given somehow a point there, it is very hard to come up with an algorithm where you again come to the same point. That's perhaps one point, one reason. Another reason is, suppose I have 2 points here. Okay, I have taken 2 points here, then there is no way I could tell that this is mapping to whether this point, this everything looks same, everything is looking absolutely same. Okay, you have the robots which are manufactured with the same features, and then you want to find out, assume that there is one more twin which does internally the same thing, you want to find out the same mapping, there is no way you could figure it out. Similarly here, if there are 2 points, you cannot distinguish them in any way and say for sure that this exactly maps to the pixel location at given so and so. Okay, that's why you could say now intuitively that whatever point you want to make as a key point should not be coming from a uniform region, right? That much we can say. Then suppose I give you now a point here as my key point. What's the problem now? So you could at least tell that, well, this point is somewhere, assume that I have another image, all these points could have the same mapping, but where is it failing? You cannot really say along this line where where it belongs to, right? That's the problem. Same is the case even if I give you a point here, then you could say, well, this point belongs to somewhere here, but you can't really say whether because all these windows, if you take, they are all identical, there is no way you could say. So when there is an edge, okay, you could perhaps localize it to the edge. Okay, that's what I think that's what you mean when say it's not as bad as a uniform region, but it's only when you have a point here that you could say for sure that this is so. In other words, the you should have that point should have gradients or uniqueness in terms of its surroundings in both x and y directions, that it should have. Then that's an good candidate for being an edge. Okay, you call it as a corner here because this has nicely carved out like this here. Okay, then that case it is a corner, and it could not necessarily a corner. That's why I was not saying earlier, even if you have some textural variations around that point where you could uniquely see that point. Okay, I have a design here, let's say some design is there here. Okay, and that design is unique here, and then if I take some point here, still that's a good point. There is a textural variations around that point where for sure corner points are good points, but corner points are not the only points, where within the surrounding region there is some textural variations, let's say. That's one way of having a distinction there, uniqueness there. Those points also are good candidates. Okay, so corners point is pretty clear here. Anyway, this we will postpone its discussion to a little later point of time for a detailed discussion. Corner, what we are mean by saying corner here is it's a sharp turn of contours you have. They are used in shape analysis and motion analysis. These are the points that you take. Okay, that's what dominates our perception of 2D shapes in practice. And we by the way, we are not worried about here RGB images as such. Now we are okay. This you could certainly consider grayscale images are good enough for us here, okay, to discuss it. Maybe color, when you have color, that's what we are not considering in our discussions. Suppose if you have color variations also, okay, that's also is something you could take a look into and consider in the constraints and in the hypothesis that we are making about the desired properties. But for now we are restricting ourselves for grayscale images. Okay. Now there is a very another interesting name that is there. Again, we will come back to it in more detail in a lot of other places. Particularly, I would discuss about it in more detail when it comes to optical flow. Okay, that's the topic that is there for after it will come after few more weeks. Then we will discuss it in more detail. But even then we could get an intuition. Let's try to get some intuition about it. See, the problem is aperture is kind of a small hole. When you are just looking around this a small patch there, okay, that is when you can't see the distinction between that point and this point. But if I had a complete picture of the whole stuff, then I could always say that, well, from the corner it is somehow the transformation of the scaling has been taken. Then I could say that this point I would be able to figure out. But when I see key point, I need to somehow characterize. For that reason, I would take a small box around that, and I will restrict my view to just that small region. Okay, so it is like you can't see the whole scenario there. You are looking from a small aperture or a small hole. Okay, then to see, then you are looking at, let's say, the leg of an elephant. Everywhere it looks the same, but not that you could make a sense out of it only when you see the whole stuff at one go. So when this problem of ambiguity in mapping from one image to the another image is coming because of the restriction in the area or surrounding region that you are looking at, that's referred to as aperture problem. Then you don't really know where to map it. So for example, you have a line here, okay, then you can't say where this point could go on this line. On the other hand, well, I don't, I have, this is another thing I have, and then to find out if I have, if you give something like this, then I could say this would go to this region. So whatever points we are getting here is clear, that's good enough. For example, motion vectors are ambiguous at an edge. We are just slightly rephrasing what you only mentioned. Locally, normal component can only be determined, tangential component cannot be determined. Okay, this again you look at in terms of an edge is there. Here is also an edge. I have taken a point here. See, this way you could say that, well, this point will be here on this part only. Okay, this you could say. So that means normal component to the edge, this is a normal. So you can give where it get maps, normal component can be said, but the tangential component, it can be any point across the edge. Okay, that's all it means. I think the way it has been, again, by the way, I took these slides from Professor Aaron Bobbick's lecture, and maybe a few other sources also I have combined. So these are not my own slides as such. I'm just using it for the sake of explanation. I'm using these slides here. Okay. So hope this point is clear. When you have an edge, you could say, for example, when I give you a point here, I could say it will be somewhere here. So in this direction, I can tell on the edge, it would be somewhere here, I could tell, but here I cannot tell. That's all it is saying. Okay. Hope that is clear. Then the next question would be, okay, so far we have thought about it's good to have corners. That's what we arrived at. We have also discussed on why we need some key points, and we have also discussed about what are the ideal properties of these corners. Okay, the and our key points, and we arrived that corner points are good. And of course, you will see later, at least in this algorithm, this is called as corner detection only. If you look at Harris, what we are going to, there is a method first proposed by Moravec in 1980s, And after that, in 1988, Harris and Stephens, okay, poor fellow, probably he happens to be the supervisor of Harris. That name is no more carried out. We simply call it as Harris corner detector. Okay, this is again the comment I'm borrowing from Maran Bobbick's lecture. Okay, so Harris, you call them as corner points, but later, as I mentioned, the moment we go to the next descriptor, more advanced descriptor called as shift descriptor, we would call it as key point rather than corner point, because there could be other points which not necessarily are corners also as the points for representing the image. Even if you are using some deep learning based recent algorithms, there also you would be taking these points and doing something else. That is also quite possible using deep learning based approaches. Okay, so this is something now. In the After this, we would be discussing about one way of computing these corner points. That's in particular, anyway, say computationally this paper is having a lot of advantages compared to Moravec paper. So we are skipping discussion about the Moravec. Right away we are going to discuss all the features of it and how it does in this paper. It's Harris corner detector is something we would be discussing. So see you all guys.